Hello guys, welcome to another video in our series on linear algebra, and today we will be discussing the inverse matrix method, which is essentially a method for solving linear equations using the inverse matrix. So we have our system of linear equations here, and we have a way of representing that using the coefficients matrix, the variables matrix, and the constants matrix. So if we write it out, it looks something like this. We have our coefficients, -2, multiplied by the variables x and y, and the results, which we call the constants matrix, on the right side. Now there is an easy way to find x and y from this, simply by multiplying the constants matrix by the inverse of the coefficient matrix. So let's find the coefficient matrix first, the inverse of the coefficient matrix, and we do that by first finding the determinant of this matrix. And this is a simple 2 by 2 second order determinant, so this equals to 6 minus 35, or that gives us -29. Now the determinant is non-zero, so that means we can continue with our calculation since the inverse exists and it can be found. Up next, we're going to find the coefficient of the coefficient matrix, and it's also quite simple. So it's 1 over the determinant, which is -29, and then we just calculate very quickly the coefficients. So it's -2. Remember, we cross out the row and the column, and the last remaining term is going to be the coefficient of the term we're looking at. So it's -2 in this case. Here it is 5, 7, and -3. Now we also have to take into account the matrix of symbols. That means that we have the first positive term and the second is negative, so it's -5, and then it's negative first term in the second row and the positive second term, so it remains as -3. Now you can see that this coefficient matrix is going to give us positive integers once we multiply it by the negative determinant, or, well, we actually divide it since it's 1 over the determinant. Now let's find the transpose of our coefficient matrix. So we flip it over, and we have -7 here, -5 below, and we have -3, and it's all in the same old place. Now the inverse matrix will look like this. So it's 1 over -29 multiplied by the transpose coefficient matrix. So now that we have found the inverse matrix, we can multiply it by the constants matrix to obtain x and y. I suggest that you do not multiply the matrix by the determinant just yet, since that introduces some rather inconvenient numbers that you will have to deal with, since you see we'll have to multiply that by 40, then add and subtract all of that business. So let's just keep it this way for now. All right, so let's start by writing our inverse matrix again. 1 over negative 29 multiplied by negative 2, negative 7, negative 5, and negative 3. And we multiply that by our constants matrix. And let's see what we get. So if you remember, the multiplication happens like this. We multiply the first term of each matrix by the second term of each matrix in their respective rows. So first row by this column, and then the second row by this column. And that gives us our variable matrix with x and y. Now let's calculate that, and we have negative 80 minus 7 in the first term, and second term is negative 200 minus 3. And we multiply that by 1 over negative 29. That gives us negative 87 and negative 203 multiplied by 1 over negative 29. Now, if you do division, dividing 87 by 29 and 203 by 29, as you can see, both of those numbers are negative, in fact, so we're going to have positive integers, and the answers will be 3 and 7. And just like that, we found the answer to the solution to this system of linear equations. Now we can easily check this if we substitute 3 and 7 into the equation. So we have negative 9 plus 49 equals 40, and we have 15 minus 14 equals 1. So we are indeed correct, and this is the answer. All right, so here's a little problem for you to try and figure out on your own. And we are going to make a follow-up video to demonstrate the solution. However, right now, I encourage you to do your best and try to solve it on your own. Thank you for watching. As always, stay geekly, like and subscribe, and we'll see you soon.